All right, so in this video, we're going to go ahead and combine both chapters 11 and 12. So this is chapter 11 is dealing with metallic bonding. This will be very brief. There are only two things that I really want to focus on in chapter 11, and that's two different types of metallic bonding. This includes the free electron model and then band theory. So we'll talk about those in just a minute. And then we'll go into more detail of chapter 12, which is dealing with ionic bonding. And there's a lot more material that I want to talk about in chapter 12, really, than what there is in chapter 11. First thing I want to mention, again, I'm only interested in us covering the couple of bonding theories associated with metallic bonding, and that's the free electron model and then band theory. We're going to skip everything else that's in this chapter. So it goes into some detail with regard to packing of metals. This is basically a rehash of what you probably covered in general chemistry with regards to crystalline solids and the metallic form in general. So I really don't want to go into more detail with that. I don't think that it provides especially significant addition to what we cover in this course or what you might have experienced in the past. This also goes for the discussion on X-ray diffraction. So unless you're going to go into a field in which you're actually applying X-ray diffraction, I don't find it particularly useful for us to go into a brief discussion with that. Instead, I might suggest hands-on experience if you have the opportunity to go into some research with one of the labs at UF, or alternatively taking a crystallography course. If you're interested in talking about crystallography, I'd be happy to have that discussion with you. I do actually teach an introduction to crystallography and diffraction course as well. But for our inorganic course, I find it more important for us to focus on bonding theories than it is to go into crystalline structures. We will discuss a bit about unit cells and crystal structures whenever we get into chapter 12 with ionic bonding, though. So you will still get some experience with that. We're just not going to go into so much detail with regard to the theory of a diffraction experiment. All right, with that being said, let's go ahead and get started. So I want to start off with just discussion of the free electron model of bonding, of metallic bonding. This is what you're already accustomed to. In general chemistry, we talked about this electron C model, where essentially we have metal cations that reside in the sea of electron density. The idea here is that those delocalized electrons, these are the valence electrons of your metals, they're delocalized and allow for a free flow of the electron density, or in other words, a flow of charge within that system. This does help to explain, or can effectively explain, a lot of properties of metals. One, the fact that they are electrically conductive. So if we have free electrons that are in the system, obviously it's going to permit the flow of electrons through that system so it can conduct electricity. It also can effectively explain the ductility, so the fact that you can draw metals into thin wires, as well as the malleability, the ability to hammer a sheet or hammer metal into a very thin sheet. So they're easily manipulated, well, maybe not easily, but they can be manipulated without breaking the structure itself. So this has to do a lot with the close packing of the atoms that are in that system, and then also, of course, as mentioned, the delocalization of electron density. Now, the way that we ascribe that delocalized sea of electron density is due to the fact that our metals have low ionization energies. So we can think of our metals as losing all of their valence electrons and being individual metal cations associated with nearest neighbors and surrounded in the sea of electron density. Can also be thought of comparably to a gas cloud, so an electron gas cloud, which is the way that your book describes it. We're not going to go into so much detail with mathematics associated with this. We're going to take this at a pretty low level in terms of our discussion associated with the electron C model, and we'll go into a little more detail with regard to band theory. So the free electron model is an acceptable first approximation for our highly metallic metals. So on the far left-hand side of the periodic table, especially group 1 and group 2, this is an acceptable model for describing the behavior of these metals. However, once we get to the transition metals, this model really tends to fail. And that's because we have the d orbitals, which are more compact, so they are less shielded in terms of their electron densities, and this leads to a situation in which we have contraction of those orbitals and more covalent nature in terms of the bonding with other metals that make up the extended solid. And that's going to lead us into a discussion of band theory. Band theory is essentially an expansion on molecular orbital theory, except now instead of looking at a discrete system, we're going to look at an infinite system. So the question becomes, what if we start off and we just have two atoms that combine? And we can, of course, draw a molecular orbital energy level diagram associated with that. And then what if we have two additional atoms that come into close proximity in order to bond with that system? And that's what we're going to develop here in just a moment in order to express band theory. So in order for us to discuss band theory, what we're going to do is we're going to start off and just consider a dilithium species. So we understand in this simple example, we of course have we have two s orbital as the valence orbitals. So we have two 2s orbitals. These orbitals may combine in phase or out of phase with one another. So we have bonding orbital or our anti-bonding orbital. From here, if we now consider what if there are two lithium-2 that come into close contact with one another? So what if we have the bonding in order to start forming a linear system? And we're just going to stick with linear for right now. Of course, in an extended solid, we're going to talk about infinite dimensions in all three dimensions. But if you consider a linear system, we have the possibility in which, we have two lithium-2s now. So let's consider two lithium-2s. We have our molecular orbitals for each of the lithium-2s already identified. So we have completely in phase. When we bring a second lithium-2 into the system, it can also be in phase with the initial system that we have, which would be even more stabilized. So we can have a decrease in our energy in which we have our four lithiums that are all in phase with one another. Or alternatively, our second orbitals could be out of phase with one another. And this would produce two bonding interactions and one anti-bonding interaction. To be clear, what I mean by that is we have our first lithium-2 is in phase, and our second lithium-2 is out of phase with the initial one. So we have two bonding interactions and one anti-bonding interaction. So this is going to be slightly destabilized from where we were initially. And then up here, we have the possibility in which we can have this anti-bonding interaction. So we get two anti-bonding and one bonding interaction. So this will be slightly stabilized from where we were of strictly anti-bonding. Or we can have completely anti-bonding. And the idea, what you're going to notice, is that our orbitals are getting closer and closer in energy to one another. As we go to an infinite number of atoms that are in this system, these orbitals are going to continue to split. And we'll have a situation in which we produce essentially a band of orbitals with no significant difference in energies between each of these orbitals. The idea of band theory then is based upon the separation in the bonding orbitals versus the anti-bonding orbitals. For our metals in particular, the band gap, so that's the separation between our bonding orbitals and our anti-bonding orbitals, or what's referred to as our valence shell and our conduction shell, or valence band and conduction band. So we'll have valence band. These are our filled orbitals, the bonding orbitals. And then we have our conduction band. The difference in energy between these two bands then, I'll call this delta E, is equal to the band gap. And in particular, we can define the behavior of extended solids, whether they're electrical conductors, insulators, or semiconductors, based upon this band gap. So how far apart our valence band and conduction band are from one another. So let's go ahead and look at the examples that are associated with those three types of systems. All right, so the different types of conditions that we have are our situation in which we have no band gap. So we have a continuous band that spans both our valence and conduction bands. In this situation, there's a free flow of electrons from the valence band into the conduction band, which is what's the genesis of electrical conductors, so the ability for electrical charge to flow through that system. Or in other words, you have easily accessible, unoccupied molecular orbitals that allow for the flow of electron density through the system. So these are electrical conductors, and these are generally our metals. On the opposite side of this, we have a situation in which we have a large band gap. And these are going to be electrical insulators because we have conduction orbitals that are inaccessible. They're too high in energy to have the promotion of an electron into that conduction band. So these are going to be our electrical insulators, and these are generally going to be our non-metals. In the intermediate system, we have an intermediate band gap, and these are going to be electrically insulators at low potentials or low voltages, and will be conductors at high voltages. So these are known as semiconductors because they have that tunable ability, or that tunability to convert between insulator and conductor. So in their normal states, so in the standard state, they would be electrically insulators or electrical insulators, but then upon application of a high potential or a high voltage, we have the promotion of electron density into our valence band, which allows for these systems to be electrical conductors. Obviously, semiconductors are incredibly important. It's a huge field, especially whenever we're talking about computers and other electronic devices. Because they have the ability to tune back and forth, allows for the formation of basically your logic circuits. So it's a yes or a no, systems on or off, with the application of electrical charge or the potential in that system. With our semiconductors then, of course, this is an entire field in and of itself, where these are defined based upon their Fermi level. So this unit is E sub F is the Fermi level. In an intrinsic semiconductor, so an intrinsic semiconductor is going to be a system in which we have that intermediate band gap, and our valence band is completely full, and the conduction band is completely empty. Our Fermi level for an intrinsic semiconductor is exactly half of the energy difference between our valence band and our conduction band. We can also tune our semiconductors by doping them. And doping just means that you add a little bit of an impurity in order to change the properties of that system. And there are two different types of doping methods for semiconductors. These are referred to as indoped, or you can think of this as negatively doped systems, and p-doped systems. So in indoped semiconductors, we're going to add a little bit of an impurity of generally a group 15 element. So our intrinsic semiconductors are necessarily going to be group 14 elements. Silicon obviously is the most common that you encounter. So adding a group 15 element is going to lead to a little bit of electron occupancy at an energy level that's closer to our conduction band. What this does is it leads to a Fermi level that's a bit higher, but we have electrons occupying orbitals very near that Fermi level, or occupying energy levels very near that Fermi level. So this will be an in-doped system. And I don't really care for you to go into much more detail than what we're talking about right now. Just identifying in-doped versus p-doped, and understanding in-doped means that we have additional electrons that are put into our system. So we have electron density that's closer to that Fermi level. In other words, we have a smaller gap between our new valence band and our conduction band. P-doped can be thought of as positive doped. And in this case, what we're going to do is we're going to add a little bit of an impurity of a group 13 element. So we have one too few electrons in order to occupy our valence band. And what this does is it leads to a situation in which we have unoccupied energy levels that are nearer to our valence band. So we essentially bring the Fermi level down by having some unoccupied energy levels nearer to our valence band. So this is p-doped. And again, I'm not going to get into all the physics that's associated with this. Semiconductors are an entire field on their own. And to be perfectly frank, unless you go into research in which you're working with semiconductors, you're probably not going to use this. But for right now, I want us to understand the underlying properties that are associated with it and how we can get in-doped versus p-doped. Just specifically, what type of dopants can be added to that system. So let's say that we have perhaps a germanium semiconductor, and we can add a little bit of phosphorus into that system, group 15 element, in order to have an in-doped type of system. Or alternatively, we could add a little bit of boron to our germanium in order to have a p-doped type of system. There are also semiconductors in which you can have stoichiometric ratios of group 13 and group 15 in order to balance out to have overall 4 valence electrons on average for your system to produce these types of semiconductors too. So a germanium arsenic combination, no, not germanium, sorry. Gallium, so a gallium arsenic combination would give you 3 valence electrons for gallium and 5 valence electrons for arsenic. At a 1-to-1 stoichiometric ratio, you can then produce an intrinsic semiconductor. All right, that's really all that I wanted to cover with regard to metallic bonding. We're now going to go ahead and switch gears and jump into chapter 12, which is dealing with ionic bonding. To start our discussion of ionic bonding, we're going to start off with just a little bit of some properties about ionic compounds, and then we're going to dive into structures of ionic compounds, and in particular, how to count the number of components that are in a particular unit cell. We'll also define unit cells as we move forward. All right, so some properties of ionic compounds. First is that the crystals of ionic compounds are hard and brittle. There's a fantastic video, actually, of Bragg, one of the founders of modern X-ray crystallography, cleaving just a huge sodium chloride crystal. So taking a sharp edge, smacking it with a hammer, and just cleanly cleaves, which is really kind of interesting, fascinating with that. The second property of ionic compounds is that they have high melting points associated with them. This is because they have a non-directional bonding that's associated with it. So of course, when we have true ionic compounds, we have point charges that now have a non-directional interaction with the other charged particles that are surrounding it. For those ionic compounds that will melt upon heating, so provided that they don't actually decompose, those that are in a molten state will conduct electricity because, again, we have those charged particles that allow for the flow of electrons through the system. In addition to that, many ionic compounds will dissolve in highly polar solvents, such as water, obviously, in order to produce electrically conductive solutions too. This is common, of course. Obviously, this is something that we already know, something that's been covered in general chemistry previously with regard to electrolytes. There we go. Couldn't think of the word. All right. Next thing I want to do now is look at some different structures of ionic compounds and introduce some terminology about how we talk about those structures. To begin our discussion of crystal structures of salts or crystal structures of ionic compounds, we first need to introduce the term of a unit cell. If we consider some gridded pattern, so if we just consider in 2 dimensions this gridded pattern, and imagine that it extends the entirety of the board, we can identify that there is a repeat unit that can be used to generate the rest of this system. And that smallest repeat unit is defined as the unit cell. So our unit cell is the smallest. It doesn't always have to be the smallest. It's typically the smallest, but it's a repeat unit, or a unit that repeats itself exclusively by translation, that can span all space, or the entire crystalline solid. Via translation. An important component of this perhaps isn't an exact definition, but an important component of this is that translational symmetry that's used to move your unit cell necessarily generates the rest of the system. So it's not just that unit cell can move, but that it moves to a symmetry equivalent position. For example, if we look at our gridded pattern, and again, if you imagine this extends throughout the entirety of the board, we could choose one of these individual squares and use that square as a generator in order to produce the rest of our system. So if I take this square and I translate it 1 unit to the right, I have an equivalent square. If I translate it another unit to the right, I have another equivalent square. And then if I translate up, we can see that I'm going to generate the rest of my 2-dimensional grid in this system. So we could define this individual square as a unit cell of our system. We could choose anything within this gridded system that repeats itself so long as it fits our stipulation that translational motion or translational symmetry will generate the rest of our system. For example, it may be less intuitive, but I could, in fact, choose a unit cell that is not along the edges of any of the squares that I already have drawn. Instead, let me choose a unit cell that's defined by having the cross in the middle of it. I can take this unit cell and I can now translate it. If I translate up, I'm going to generate. These are the external components of my unit cell. On the internal component, of course, I have still my black cross that's in the middle of that. So again, we could generate the rest of our system by choosing any particular unit cell that's convenient for us. Now, in dealing with unit cells, we can also extend this to a 3-dimensional system. So obviously, instead of just dealing with a 2-dimensional gridded system, I can look at perhaps a cube. And there are a few specific different types of unit cells that we could have generated. We're only going to focus on some of the simple ones. They're all going to be cubic in nature, so our cell edges are all equivalent in terms of the lengths associated with them. And this is for convenience. It's also for we're going to have more examples, more ionic compounds that are composed of some basic cubic unit cell with specific positions of the atoms or the ions that are in that system. So what I want to do now is focus on those different arrangements of ions or atoms in a cubic unit cell. In particular, if we start off and we identify there are exclusively atoms on the corners of our unit cell, we would refer to this as a simple cubic unit cell, or a simple cubic packing pattern. In addition to that, if instead of just having atoms on the vertices, the corners, we could also have atoms or an atom directly in the center of our unit cell. So if we have atoms on our corners and then one directly in the middle of our unit cell, we refer to this as body-centered cubic. We can also have a situation in which we have atoms on these are equivalent atoms. I want to be very clear about that. So I'm going to color coordinate these. Right now we're exclusively talking about one type of atom. So if we have atoms that are on the corners, and then also atoms that reside on each of the faces of our unit cell. So this is on the top face, this is on our right side. I'll draw one in the back. This is on the bottom, on the left-hand side, and one that's on the front, I'm going to leave unshaded right now. So that's the front face of our cube. We refer to this as face-centered cubic. So not terribly creative names, it's pretty straightforward. Abbreviations for these then, we have SC for simple cubic, BCC for body-centered cubic, and FCC for face-centered cubic. These are going to be the building blocks for a lot of the different ionic compounds that we're going to be discussing. And then we're going to talk about filling holes or vacancies within these individual unit cells by another type of ion in order to build up our ionic compounds. Before we really get into that though, I want to address how to count the number of atoms or ions that are in a particular unit cell based upon the positions in which they occupy. So if we consider going back to our two-dimensional plot or two-dimensional grid, and we consider an atom that's sitting on one of our corners. So let's choose this corner right here. We can ask ourselves, how many different unit cells does that particular atom belong to? Because the corner of our unit cell is right in the middle of that atom. So we find, of course, that there are 4 different unit cells in which that atom is a part of. That means that this atom contributes 1/4 of itself to each of these individual unit cells. When we extend this to 3 dimensions, we now have to also consider the forward and back, or top and bottom, if you want to think of it that way. So let's look at the different types of sites that are present in our unit cells and how we will have atomic contribution to the particular unit cell. So let's start off with a simple example where we have a position that's entirely inside of our unit cell. So if we have an atom that's not on any of the faces, it's not on an edge, it's not on a corner, but it's somewhere that it's completely contained by our unit cell. That might be right smack in the middle, or alternatively, it might be some position that's just within the unit cell. Obviously, it's only contributing to that one unit cell, and we refer to this as a body site. So I'm going to choose the example where it's right in the center. So a body site is going to have a contribution of 1 to that particular unit cell. And this is obvious because, of course, it's not shared by any other unit cells. Let's consider a different system then. So what if we have an atom that resides on a face. So I'm going to choose this right side face. And if I have an atom that's in this position, I can draw the other unit cell that it belongs to. And it becomes obvious then that there are two unit cells that share this one atom. So face sites are going to contribute 1/2 to each unit cell. And then we can look at edge sites. So I'll choose this top right edge over here. I can draw a unit cell out to the right-hand side. But we see that this only takes up half of this atom. This atom is also shared with two unit cells that are above this plane. So this means that an edge site is going to contribute 1/4. There are 4 different unit cells in which this atom is participating with. If we then look to one of our corner sites, so if we just take our simple cubic example, this drawing can get a little out of hand, but I have 2 unit cells that are going to be behind it. I have this unit cell that's over to the right and down here, and then I have another 4 unit cells that are on the top half of this atom. So I have 1, 2, 3, 4 in the back, 5, 6, up forward, 7, and 8. And that might be difficult to follow, but try and play with it to try to draw the diagram. If you draw all 8 of those unit cells, you can sometimes get that particular position lost. But for right now, you can take my word for it, or draw it yourself. So this means that a corner site is going to contribute 1/8 to our particular unit cell. Based on that information, let's count how many atoms are in each of these 3 cubic systems that we've already identified. So if we look at our simple cubic example, we have 1, 2, 3, 4, 5, 6, 7, 8 atoms that all occupy corner sites. So 8 times 1/8 gives us 1 atom per unit cell. If we look at a body-centered cubic system, we have 1, 2, 3, 4, 5, 6, 7, 8 atoms in corner sites. So 8 times 1/8, plus we have 1 atom that's in a body site. So 1 times 1, and this gives us 2 atoms per unit cell. And then if we look at our face-centered cubic example, we have again 2, 4, 6, 8 atoms in corner sites. And we have 2, 4, 6 atoms in face sites, which gives us 4 atoms per unit cell. Counting the atoms or counting the ions that are in a particular unit cell is going to be important, because when we start looking at the structures of ionic compounds and try to identify the formulas based upon a crystal structure, it's going to be necessary that we correctly identify the numbers of each of the ions that are present within that system. So what we're going to do now is go ahead and take a look at some different examples of crystal structures in order to count the ions that are present, and also identify the positions that are being occupied within those systems. All right, so let's go ahead and look at some of the different crystal structures of ionic compounds that we're oftentimes going to run into. The first one I want to start with is a cesium chloride system. So in this case, I have chlorides that are occupying the vertices, or the corners of a cubic unit cell, and then I have one cesium that's directly in the center of that unit cell. We can define the system then based upon the arrangement or the lattice that our chloride ions span, and then defining the holes or the vacancies that are occupied by cesium. We would describe this system as being a simple cubic lattice of chloride ions and the cesium cation occupies the cubic hole. And we define the cubic hole based upon the fact that this is in the center of the cube. So it has a coordination number of 8 for that particular cesium. So cesium plus occupies cubic hole. Our coordination number is defined as the number of nearest contacts, so the number of nearest neighbors that you have for a particular system, and the coordination number of cesium is equal to, in this case, we have 1, 2, 3, 4, 5, 6, 7, and 8. So the coordination number of cesium is 8. For the chlorines, it can be a little more difficult to visually inspect and identify how many or what the coordination number is for the chlorine or for the chloride. But let's go ahead and do a visual inspection, and then I'll introduce another method for determining coordination number of your other ion. So one thing that I want to emphasize is that every corner of our unit cell is identical to every other corner of that unit cell. Because if you consider the relationship by translation, if I translate this unit cell 1 unit to the right, that means that this left-hand side, so this ion that we have in the corner, the left-hand side is pointed in toward this unit cell. That necessarily means that it's going to be the equivalent position as over here. That also means that this atom is necessarily equivalent to this particular position that we just identified, so where we started from here. And that tells us that the coordination environment of this ion in the back, its forward right-hand component, is also oriented in such a fashion. So we have another coordination in this bottom right-hand octant of that ion. Basically, we would have to evaluate every single octant, but it's easy because, again, this is related by translational symmetry to every other corner in our system. So we identify the coordination number of each atom that's in this, or each ion that's on a corner, which has a 1/8 contribution to this individual unit cell. We have 1, 2, 3, 4, 5, 6, 7, and 8. So the coordination number of our chloride is necessarily also equal to 8. Another way in which we can identify our coordination numbers is by looking at a relationship between the coordination numbers of our cations and anions and the charges on those components. So we can say that the charge, let's call it, here we go. So the charge on our anion divided by the charge on our cation must be equal to negative coordination number of our cation divided by the coordination number of our anion. Alternatively, you could write this as just the absolute value of the charges. So the magnitude of the charge on our anion divided by the charge on our cation is equal to the coordination number of the cation divided by the coordination number of the anion. In this case, we know cesium and chloride are each magnitude of 1 for their charges, so the coordination number must be equivalent to each other. We can also determine the total number of ions that are in this. First off, we know for a particular unit cell, it has to have the empirical formula. So the empirical formula of a unit cell must be equivalent to the empirical formula of the salt that we're talking about, the ionic compound that we're talking about. So we know that we must have a one-to-one relationship of cesium to chloride in our system. We can count directly the number of cesiums and chlorides that are in it by using the relationships that we talked about previously. So we have one cesium that occupies this body center, so it's a body site, and there are no other cesiums in our system, so there's one cesium per unit cell. And the number of chlorides, we have 8 corner sites that each contribute 1/8, so we have 1 chloride in our system as well. Obviously, this matches with our empirical formula of cesium chloride and what we expect. Similarly, our charges and coordination number match based upon the relationships that we've shown here. All right, the next example I want to look at then is sodium chloride. This figure may look really nasty to you. Your book has better drawings, not even perhaps, has better drawings of it in figure 12.1 or also in table 12.1 as the first entry there. I have bolded the unit cell, so the cell edges of our system, to try to make it stand out a little bit more, but that still may not have helped too much. In this case, I've drawn my sodiums in black and I have my chlorides in green. So what we can identify from the system, the positions of our chlorides, we have chlorides that are occupying every corner site as well as every face site in our system. So we would say that the lattice of our chloride ions, so the chloride lattice, is face-centered cubic. Since, again, we have a cubic unit cell and all of the face sites that are occupied. We can then define the positions of sodiums relative to the types of holes that are present in our system. So in a simple cubic system, we only have one type of hole that's possible, and that's a cubic hole, right in the center of the body. In a face-centered cubic system, we have 2 different types of holes that can be present. And we have those exemplified through these 2 examples of sodium chloride and then the zinc blende crystal structures. So in sodium chloride, we can define octahedral holes in which our sodium cations are occupying. And we identify its octahedral based upon the coordination environment around the ion that occupies that particular position. I find it most convenient to look at the body center of this system. So right here in the middle, we have a sodium cation, and it's coordinated to 1, 2, 3, 4, 5, 6 chloride ions. They're the chloride ions that reside on the faces of our cubic system. So we say then that sodium occupies the octahedral holes. And it turns out that it occupies all of the octahedral holes. The other octahedral holes are on the edge sites. So we can define, again, that environment. If we choose, let's say, this sodium in the back here, we have coordination 1, 2, so that's these 2 here, 3, 4, 5, and 6. So again, we can see that octahedral geometry about that sodium cation. This also allowed us to easily calculate or to count the coordination number for our sodium. So we can say the coordination number of sodium is 6. Since sodium and chloride both have the same charge, it means that the coordination number of our chloride must also be 6, and we can also directly count that from one of our particular positions if we wanted to do that. I find the face site a little bit easier to count rather than the corner site, but you should practice looking at both of those. One thing that I also wanted to note out of the 2 systems we looked at so far is the ions in these systems are actually interchangeable. So it's not important that we defined a chloride a chloride simple cubic lattice with cesium occupying the cubic holes. We could also identify a cesium simple cubic lattice with chloride occupying the cubic holes. And I'll try to draw that real quickly just to exemplify what I mean by that. If we consider the lattice that would be formed by the cesium, so if you extended this unit cell, you would have, of course, a chloride directly above. We would get one to the back over here, occupying the center on the side over here, and so on and so forth. That's behind this red position. That's fine. And what I hope you notice then is that this chloride is now occupying a body cubic site, or a cubic hole, in a simple cubic cesium lattice. Comparably then, for sodium chloride, we could also switch out the ions. And I think it might be a good exercise for you to draw out an additional, however much you need. You don't really need to draw a full additional unit cell, but build it out so that you can generate the sodium face-centered cubic lattice and prove to yourself that the chlorides occupy all of the octahedral holes in that sodium face-centered cubic lattice as well. Let's go ahead and turn our attention now to zinc blend. So this is the other type of of holes that can be occupied in a face-centered cubic type of system. So in this case, I have zinc drawn in black, and I have sulfur, or the sulfide, drawn in blue. We see again that sulfide is occupying, or has a face-centered cubic lattice. It occupies each of the corner sites as well as every face in that cubic system. So sulfide is face-centered cubic lattice, or in a face-centered cubic lattice. And then our zincs occupy half of the tetrahedral holes. We can identify their tetrahedral again because of the coordination environment around each of those zincs. And I've tried to draw this as clearly as I can. Your book has, again, a much better picture in table 12.1. It's the second entry under AB types of structures. But we can see that we have a coordination number of 4 for each zinc. So coordination number of zinc 2+ is 4. And since we have equivalent charge on sulfide, the coordination number of sulfide is also 4. You also should be able to count that. So I find it most convenient to look at an individual face site because these are the easiest to calculate. It has the fewest number of comparable or symmetry equivalent positions. So for instance, this bottom face, the top half of the ion has a coordination number of 2. And then its symmetry equivalent position is going to be the bottom half of this top face. So if we translated up 1 unit cell, we see that the bottom half also has a contribution of 2, or a coordination number of 2. So we have a coordination number of 4, and it's also a tetrahedral environment about that particular ion that we're dealing with. Let's go ahead and count the number of ions that are present in our system as well. And we'll do it with zinc blend, and then we'll come back to the sodium chloride since I skipped that earlier. So the number of zincs that are present is equal to, these are of course again drawn in black, and they are fully inside of the unit cell. Note that they're not body centered, however they still don't share unit cell with any other component. And again, we can see this because of the bonds that are drawn, so the coordination environment. So we get 4 times 1, which of course gives us 4. The number of sulfides that are present in our system. We have 8 corner sites that all contribute 1/8, and we have 6 face sites that each contribute 1/2, which gives us a total of 4 sulfurs that are in our system as well. We can define the number of formula units in our unit cell as Z. So in crystals, or in crystallography, we define Z as the number of formula units per unit cell. So this is formula unit per unit cell. We have, in this case, 4 formula units. The formula unit, of course, is ZNS. We have 4 zincs and 4 sulfides, so 4 formula units. in one unit cell. So Z in this situation is equal to 4. If we look at our sodium chloride example now, we have the number of sodiums that are in our system. Our sodiums are drawn in black. We have one body-centered site, so one body site. And we have 2, 4, 6, 8, 10, 12 edge sites. And edges all contribute 1/4. So this gives us a total of 4 sodiums that are in our unit cell. Number of chlorides we know must be equal to 4, but let's prove it to ourselves. Chlorides, we have 8 corner sites, so 8 times 1/8, and we have 6 face sites, so 6 times 1/2, giving us 4. Again, we need to find number of formula units per cell is then equal to 4. We can have situations in which we have a face-centered cubic system, so a face-centered cubic lattice for one of our ions, and then all of the tetrahedral holes filled as well. An example of this is fluorite, so CaF2. I highly recommend that you take a look at this. It is on page 395, so table 12.1, under the AB2 entry. So let's go ahead and return to a discussion in regards to lattice energies. First off, I want to reintroduce this and just remind you that the lattice energy of an ionic system is the enthalpy of the conversion of gas phase ions into a solid state crystalline lattice. So previously, whenever we discussed this, we said that the energy is directly related to the Coulombic attractions between those ions. And to a first approximation, this is an acceptable description of what's going on with the system and a method to evaluate relative energies of different lattices or lattice enthalpies. So if we consider just an ion pair, then it becomes obvious that the overall energy of the system is just going to be related to the Coulombic attractions if we consider only that individual pair. However, when we're talking about extended solids, we're talking about the crystalline state. This is an infinite solid. We don't just have the nearest neighbor interactions. It's not just an attractive force between a cation and the neighboring anion. In addition to that, we have repulsive forces between this cation and the nearest other cation. And then we have attractive forces between the cation and the next nearest anion, and so on and so forth. So the total energy of our system, so the total lattice enthalpy for an actual crystal, is going to be related to the sum of all of those attractive and repulsive forces. Luckily for us, we don't actually have to go through and calculate every single one of those interactions. Instead, we're going to use what's called the total lattice enthalpy or total lattice energy. And this is going to include a term called the Madelung constant. The Madelung constant is a term that's included into basically a version of our Coulomb's law to compensate for the attractive and repulsive forces in long-range systems. Necessarily, the Madelung constant will be dependent on the crystal structure. So, for instance, I only have a line of ions that are shown here. And we can see how if we choose this cation on the far left-hand side, we have an attractive force between this nearest anion. But then we have repulsive forces between these two cations. And then, again, attractive forces here and repulsive forces, and so on and so forth. If you were to extend this into a two-dimensional network, well, we would also have the attractive force between the anion that's below and above in the plane of the board. And if we go to three-dimensional system, we also have the ions that are coming out of the plane of the board and going into the plane of the board. What I've now effectively drawn is rock salt, or sodium chloride structure. So we would have a face-centered cubic lattice of our cations. Our anions fill all the octahedral holes. However, if we had a simple cubic system, this is necessarily going to give us a different type of interaction. So simple, for instance, cesium chloride, simple cubic with cubic holes. that are filled. There's necessarily going to be different extent of interactions, and therefore a different Madelung constant associated with it. Luckily for us, the Madelung constant is exclusively related to the structure and not the actual identity of the components. So let's take a look at the total So let's go ahead and take a look at the total lattice enthalpy equation, including Madelung constant. So to calculate our total lattice energy, we can use the Born-Land equation, which states that U naught is equal to A, which is the Madelung constant, times Avogadro's number in sub A, times the charge on your two ions, so charge of your cation times charge on your anion, times the charge of an electron squared, divided by 4 pi epsilon naught, which is related to the permittivity of free space in a vacuum, times R naught, which is the distance between your ions in your system, times this component, this factor that we have, 1 minus 1 over N, where N is the average Born compressibility factor. N is directly related to the electron configuration of your ions. So if you look on page 399 of your textbook, this is table 12.2, includes the Madelung constant, so the term for A, which is directly related to the structure of your ionic compound. And then 12.3, so table 12.3, has the Born compressibility factors that's, again, based upon the electron configuration of your ions. When you have ions that have different electron configurations associated with them, for instance, let's think of something like cesium fluoride. Fluoride, of course, is going to have a neon electron configuration, whereas your cesium is going to have a krypton electron configuration. Yeah, good. The term, the Born compressibility factor for a neon electron configuration is 7, whereas that of a krypton electron configuration is 10. So we're going to take the average of those two terms, so we'll get 8.5 as our N value if we were calculating the lattice enthalpy or lattice energy of, say, cesium fluoride. Other than that, this is really straightforward. It's just introduction of another equation that introduces two additional terms that we haven't used previously. That's the Madelung constant, and again, I want to emphasize conceptually, the purpose of the Madelung constant is to compensate for long-range order of your system and those long-range interactions, both attractive and repulsive forces. Your book goes into more detail expressing how this term is actually derived based upon the particular ionic structure that you're dealing with. But we're not going to go into as much detail associated with that. And the other is this Born compressibility factor, so this N term. I want to make one other quick note. Whenever I work with the Born-Land equation, I prefer to use the terms Q, so Q1 and Q2 instead of Z for the charges on my cations and anions. Your textbook, of course, uses Z plus and Z minus in order to indicate the charge on the cation and charge on the anion. The problem I have with that, of course, is that a capital Z is used to denote the atomic number of your system, not the charge of the system. Q is typically used to denote charges. You'll see these used interchangeably depending upon what textbook or what reference it is that you're looking at. Just note that they are equivalent expressions. I just feel like using Q is a little more intuitive and less likely to trip you up whenever you're working through these problems. Your textbook does a couple of examples associated with this too, so take a look at those and make sure that you don't have any issues with this. Obviously, though, this is just algebra, so there's nothing special. We've introduced a new concept with regard to Madelung constant and Born compressibility factor, but other than that, this is now just math. Simple math at that. All right, cool. So from here, we're going to go ahead and move forward and get into some other properties of ionic compounds. All right, so a couple other things I want to emphasize at this point. First is that lattice enthalpies are experimentally determined. They're experimentally determined based upon thermodynamic cycles related to the Born-Haber cycle. So this is something we've already looked at, and this is related to, of course, like enthalpies of formations. So we understand that we can use Hess's law, which states that the overall enthalpy of some reaction is necessarily just the sum of individual steps in order to derive or build up that overall reaction. So all these are experimentally determined, and then the equations are developed based upon that experimental evidence. The other thing that I want to talk about just briefly is related to enthalpies of precipitation. So we can talk about, let's say, precipitation reaction. This, of course, is going to be directly related to solubilities. And if we consider an enthalpy of precipitation, we're necessarily going to be looking at some reaction involving aqueous ions, and then the formation of a solid or precipitate. So generically, we can say something like alpha of m in plus aqueous plus beta of x y minus, just arbitrary letters, it doesn't really matter right now, aqueous goes to form our salt, our solid component of m alpha x beta solid. And then this enthalpy is the enthalpy of precipitation. Now, this probably doesn't seem very obvious. Like, why the hell would we do this? We talked previously about the lattice enthalpies. We've talked about the enthalpies of hydration. That's actually what I want to bring back up right now. Enthalpies of hydration. So how is an enthalpy of precipitation related to these other components? Well, I want to emphasize at this point that the enthalpy of, or the lattice enthalpy is, of course, the energy change, the energy that's released when we go from gas phase ions to the solid crystal lattice. So what that means is that we can identify a reaction. We say U sub O, so the lattice enthalpy of this reaction then is going to be, we have beta of x, y minus in the gas phase, and alpha of m in plus in the gas phase. Well, finishing up this cycle really isn't that difficult, because we know that going from the gas phase to the aqueous phase for a particular ion is just the enthalpy of hydration. So the reverse of that is necessarily the negative enthalpy of hydration, and it's necessarily going to be negative alpha times delta H of hydration for this particular ion. And then for our X, we have negative beta times enthalpy of hydration for this particular ion. What we find then is we can write an equation for the enthalpy of precipitation of m alpha x beta is equal to, we have negative alpha times the enthalpy of hydration of m in plus minus beta times the enthalpy of hydration of x y minus plus the lattice enthalpy of m alpha x beta. And the point of doing all of this is showing that there's a direct trade-off between the enthalpy of hydration of a particular ion and the lattice enthalpy for determining whether we're going to have the formation of a precipitate or if our salt is going to be a strong electrolyte, so dissociate into the individual ions. So we can go through this and basically reason through the different energetics associated with this system. So of course, the extent of interaction of a particular ion with water molecules around it, so the enthalpic term associated with that, as well as with our anion, versus the formation of that solid state. So is it more favorable for our ions to be surrounded by water, so solvated or aquated, hydrated, there we go, or in our lattice, a crystalline lattice? So this is only part of the story, because obviously this is only a portion of the thermodynamics that are associated with our system. We understand clearly that not only is there this enthalpic term, so that's the strength of the interactions with one another, the energy associated with those interactions, but also an entropic term. So entropy related to the extent of disorder of our system, or in other words, the number of microstates, the number of individual ways in which we can arrange degenerate energy levels, is going to play a significant role in whether we have the formation of precipitate or if this remains in an aqueous solution instead. For instance, the enthalpy of precipitation of sodium chloride is actually negative. So it would be exothermic in order to have the formation of sodium chloride from solution. However, we know, of course, that sodium chloride is readily soluble in water. So we understand that there's that entropic term that leads to a favorable dissociation of sodium chloride. I also know that we don't typically talk about an enthalpy of precipitation, especially with sodium chloride. If you were to look at the enthalpy of dissolution of sodium chloride, of course, this would be an endothermic process. And if you've ever made a solution of brine, the bottle gets cold as you're making it. So obviously indicating this is an endothermic process. However, it's still spontaneous at room temperature. So indicating again that we have that favorable entropic term associated with formation of solution. That really finishes up what I want to discuss with regard to ionic bonding and finishes up chapter 12. Getting into the next chapter, we're going to talk more about the relationship between structure and bonding, and then reactivity of our different systems as well. So until then, make sure that you're working through problems, and let me know if you have any questions.